All right, let's talk about electrolytes and net ionic equations. And the general solubilities of ionic compounds in water are shown here. And so you should have a general idea that if you have an ionic compound and it contains a group 1 metal, so if you have a group 1 metal, it says here 1A, but just group 1 metal, like sodium, potassium, lithium, etc., those are going to be soluble. Or if you have an ammonium ion, okay, is your cation, that is generally going to be a soluble compound. There won't be any exceptions to that. If you have a nitrate or an acetate as your anion, those are also going to be soluble, and we won't have any exceptions to those. Chlorides are also soluble, except for chlorides of silver, lead 2, mercury, and mercury 2. Sulfates are also quite soluble unless they're sulfates of barium, strontium, lead 2, mercury, and mercury 2. And then we have carbonates, which are not so soluble. We saw that earlier on in another video with calcium carbonate. So carbonates are going to be insoluble unless you go back to the first rule. If they're combined with a metal from group 1A or the ammonium ion, they're going to be soluble. And then finally, phosphates are going to be insoluble again unless they're combined with a group 1A metal or the ammonium ion. All right, so those are the solubility guidelines. You don't have to memorize those right away. We're going to refer back to this a couple of times. And you see the little asterisk down here. It says many hydrogen carbonates and hydrogen phosphates are soluble. So let's take a look at what we call a total ionic equation. We're going to start out with a molecular equation, which is just an equation written with each compound represented by its formula. So here we have hydrochloric acid plus sodium hydroxide gives us sodium chloride plus water. Now what we're going to do is we're going to take that molecular equation and we're going to make a total ionic equation from it. Sometimes I call the molecular equation just the ME, and I'll call this the total ionic equation like this. The idea is this, is that anything that says aqueous, okay, so that would be the HCl, the sodium hydroxide, and the sodium chloride, not the water that says liquid, but anything that's aqueous, we break it apart into its ions, okay? And now this requires a little bit of chemical knowledge, right? We know that HCl, since it says aqueous, it's made out of an H plus ion and a Cl minus ion. Then we go to sodium hydroxide, which is aqueous. It's made out of a sodium cation and a hydroxide anion. Then we go to our sodium chloride, which is made from a sodium cation and a chloride anion. And the water, we leave that the same. Why? Because it says liquid, okay? It doesn't say aqueous. So now what we're going to do is we're going to look at our total ionic equation. You see the reaction arrow is right here. We're going to look for ions that are the same on both sides, and we're going to cancel them out to make what we call a net ionic equation. And so what ions do you see that are the same on both sides? Well, the first thing that I see is chloride is the same on both sides. And then you can also see that sodium is the same on both sides. And we call those ions that we canceled out, the ones that are the same on both sides, we call them spectator ions, right? Why are they spectator ions? Because they aren't changed from the reaction side, the reactant side to the product side. They look identical on both sides, and so we just cancel them out because they're not really participating in the reaction. So once we write down what's left over, H plus OH minus gives you H2O, we can just write that down, leaving out the spectator ions, and get what we call a net ionic equation. I usually abbreviate this as net ionic equation like that. And again, it only shows the reactants and the products that are really actually changing throughout the reaction because again, the chloride ion wasn't changing and the sodium ion wasn't changing in this particular case. Okay, so example 6.8, write the total ionic, the net ionic equations for the following double replacement reaction. So again, anything that's aqueous, we're going to write out into its ions, but not the barium sulfate, right? Because that's a solid. So let's start writing down our ions. So for our total ionic equation, first we're going to put sodium. Now, we have two sodiums, don't we? So we're going to put two sodium cations, and they are aqueous, plus a sulfate ion, and that means you have to memorize that sulfate is SO4 2 minus, plus barium, which is 2 plus. How do we know that? Because it's in group 2. And we have 2 chlorides, so plus 2 Cl minus, aqueous. Then we'll just leave the barium sulfate until the end, but we've got 2 sodiums, and we also have 2 chlorides that are aqueous, and I'm kind of running out of space, so I'll just put the barium sulfate, which is a solid, down here. So here's our reaction arrow. What do you see that's the same on both sides? Well, the first thing that I notice is the 2 sodium ions, and then I also notice the 2 chloride ions. Maybe I could use a different color for those. 2 chloride ions, like that. So now what's left over when we go to write out our net ionic equation? You see that I have the sulfate before the barium. I just like to list the metal first, so I'm going to put barium 2 plus aqueous plus sulfate gives you barium sulfate. And that is our net ionic equation. This one here is a take-home problem. Let's see if we can solve it on this slide. It says figure 6.22. The liquid in the large container is a solution of solid sodium chloride dissolved in water. So that's an aqueous solution of sodium chloride. The liquid being added to the solution is of solid silver nitrate dissolved in water. So either way, these are both aqueous solutions. When the two aqueous solutions are mixed, you get an insoluble white solid, okay? Write the molecular, total ionic, and net ionic equations. Well, the molecular equation, what they're showing you here, is you have sodium chloride, that's aqueous, and you also have silver nitrate, which is aqueous. And so that's a double displacement reaction. So we're going to end up with sodium nitrate, which is a soluble compound, and then we're going to end up with silver chloride, which is a solid. Now, if you're going, well, how did you know that this is a solid? If I go back to my solubility table, just excuse me here for a second. We said that chlorides are soluble, but not chlorides of silver, right? Nitrates are soluble no matter what. And so if we go back here, where was I? That would be our this is our molecular equation. But if I break everything down that's ionic or aqueous into its ions, I end up with sodium plus aqueous plus chloride aqueous plus silver plus aqueous plus nitrate aqueous, which gives us sodium plus from our sodium nitrate plus nitrate plus silver chloride, which is a solid. I don't break that apart into its ions because it's a solid. So this would be my total ionic equation. And so now what I'm going to do is I'm going to cancel out the spectators. And so I see that sodium is the same on both sides. I also see that nitrate is the same on both sides. And so to write out my net ionic equation, I'm just going to have silver plus chloride gives me solid silver chloride like that. And that is going to be my net ionic equation.